completed his PhD degree at the University of Toronto in 1997 and was an NSERC PDF at the University of North Carolina at Chapel Hill. He began his independent research career in 1999 as an assistant professor at the University of British Columbia and is currently professor of chemistry. At UBC, he has received the SUS Teaching Excellence Award, the CNC IUPAC Award, and the CSC STREM Chemicals Award for Pure and Applied Inorganic Chemistry. His research interests bridge inorganic and polynochemistry with particular emphasis on organophosphorus molecules and materials. We welcome you, sir. I would also like to welcome the invited speakers for this session, Professor Gerhard Haegle and Professor Ramaswamy Murugevel. I now request Professor Gerhard Haegle to take his seat on the dais. May I now request Professor Gates to take over for the session's proceedings.
Thank you very much, and welcome back after lunch. It's a pleasure for me to have the opportunity to introduce Professor Gerhard Haegle from the University of Düsseldorf in Germany, and he's had a long academic career that I'm sure we can find out more about on the web. And he's asked me to keep this introduction short so we can get started right away. So I'm going to let him take over the floor, and he's going to talk about NMR and analytical studies of organophosphorus compounds, including their synthesis as well.
We do phosphorus chemistry and NMR and analytical chemistry, and we do computing. Computing is our main source of information here. What I wanted is to show you the chemistry of chiral phosphinic acid esters attached to ethane structures. I will make a substituted series with 1, 2, 3, 4 phosphorus attached to ethane, and you will see the influence of overcrowded molecules. I begin in a systematic manner how to make these compounds. This is the basis of making the esters via the Michaelis-Abusov reaction. First of all, you prepare your reagent. This is a phosphonous acid dialkyl ester. And we prefer phenyl because the compounds will be solid. And we prepare isopropyl because they form nice crystals later on. Yeah? Okay. And these are, of course, active against halogens and alkyl halides and less aryl halides to form dialkyl or aryl phosphinic acid isopropyl esters. Next slide. Oh, here it is. Yeah. Good. We have a second main reaction to establish a PC bond, and that is a Michaelis-Becker reaction. First, you start off from phosphorus dichloro compounds. You react with an understoichiometric amount or stoichiometric amount of isopropanol in the presence of dimethylamine, and you get at low temperatures, that is very important, you get the monoesters, which still have a pH active proton there. And a broad variety of compounds are available like this method here. And they deprotonate easily with sodium hydrate. Particular productions of sodium hydrate are very soluble and very suitable for this. And you get an anion. But the trick is you use tetrahydrofuran as a solvent. And then sodium is complex, and what we effectively use is a naked phosphonate anion, which is very active. This reaction is not possible, which I will show you later on, if you have protic solvents. Okay, so next one. We make that the sodium salt reacts with alkyl halogenides to form the same type of esters. And if we attach the phosphorus to a dibromoethane, we get in the first step a phosphonic acid, a phosphinic acid, with a dibromoethyl group, which is chiral at phosphorus. And you see interesting NMR spectra here, A, B, C, E, X. I will not talk about the alkyl ester functions. They are trivial. Yeah? Next spectrum. In the second reaction, is the Michaelis-Abusov reaction, the second phosphorus is attached. But now we have two chiral centers on up, and we have a meso and a racemic form, and they have completely different NMR spectra and slightly different phosphorus chemical shifts. Oh, what is it? He doesn't want anymore. Oh. Yeah, okay. Next step in our synthetic plan was to make tris substitute ethane. And this is not possible with the Michaelis-Abusov reaction. Trichloro, tribromo, ethanes do not react according to Michaelis-Abusov. So we cannot produce a 3-phosphinic acid. We need a new technique. And the new technique is called an anomalous Michaelis-Becker reaction. You have the sodium salt of your phosphonide in tetrahydrofuran, only in tetrahydrofuran. And then you can add olefinic chlorine compounds. This is a dichloroethylene. And you get this very good yields. You get directly the tris-phosphinic acid esters. Because they are chiral, you get a mixture of isomers, which I will show you very soon. In the next step, and the final step of the systematic here, we attach the phosphorus again with the sodium salt, but we react tetrachloroethylene. And tetrachloroethylene forms directly with almost quantitative yields. You see an ethane, these 4-phosphonate esters, which is a very overcrowded molecule, and no canonical rotamers will be formed, as we see soon. The mechanism is clear. We start off from the olefins, dichloro or tetrachloroolefin. In the first case, hydrochloride is abstracted, and the intermediate is a monochloroacetylene. And in this case, chlorine is abstracted, and we get a dichloroacetylene. And the next steps are very clear. They are Michaelis-Becker reactions then. We come to a monophosphinic acid of acetylene, or here a diphosphinic acid of acetylene. Our anion, the naked phosphonate anion, adds to the acetylene, forming a hypothesis that is an anion of an olefin, and it can be neutralized by the proton from the TRF to form an olefin. And here the same analogous procedures. We get 3 substituted olefins, and they are open for further access. In the left side, we come to an addition of a third phosphorus, and we find an anion which is intensively yellow colored and stable for a long time in tetrahydro. On the right side, we get a deep purple colored D-anion, a D-cup anion. Yeah? Neutralization by acetic acid will lead to the neutral skeletons of the tris or the tetrakis phosphinic acids. I go now in next step, preparing the NMR. This is a compound having an ethyl group attached to a chiral phosphorus. So what we see is in proton NMR an ABC 3X spectrum, which is textbook chemistry, I would guess. Yeah? Oh dear. Good. If you have a D-phosphinic acid, you have a meso and a racemic form. The symmetry is different, but still it holds a 2-fold symmetry, and we get complicated spectra of the type ABX twice, and we can decouple the protons or decouple the phosphorus to get very simple NMR spectra. In the case of proton decoupled phosphorus, it's just a singlet with an X2 spectrum, but it has a different shift for meso and succinic forms. The 3-phosphorus compound has 4 isomers, and all have an asymmetry which produce spectra of the type X, Y, Z if you decouple the phosphorus from protons. And in the here we see the spectra which we can expect from the tetraphosphorus substituted ethane. We have 3 isomers which give rise to XY twice spectra when you decouple the phosphorus from the protons. And we have 3 isomers, 2 isomers, which give a primitive first order spectrum of V, X, Y, Z. And finally, the highest symmetry is represented by the 6th isomer, which has just an X4 singular. Yeah? The proton spectra are textbook, good for teaching. Yeah? This is, for example, the monophosphinic acid. And we see the next one. This is a simulated molecular structure. You see the phenyl ring here. 2 protons of the methylene group are in the field of the aromatic ring current. This is a pro-R proton, and it is recognized because the coupling constant from HCP is trans to the HCPO double bond. That is an identification of the stereochemistry. The bisphosphinic acid has 2 isomers, you see. The first one is upper, the mesoform, and lower is the succinic form. And they, of course, correspond. The proton spectrum, when we decouple the phosphorus, is the AB twice spectrum, which is textbook. Yeah? But they are very different. The interesting thing is, in one spectrum, in the second spectrum, the center is alike, but the combination of coupling constants is very much different. Let us start with this one. Yeah? Okay. Here we are. That is a mesoform upper. You see in the chemical shift is typically at about 2 and 2.1 kVm. We determined it by iterative treatment of the NMR data using a program called TopSpin from Bruker, which gives very accurate data if you have accurate spectra. Okay, coupling constant. I cannot discuss all of them, but it is interesting to see. No, not again. Be slower. What is going on? I press a button and nothing happens. This one. This is next, and this is back. Okay, we tried. Thank you. Yeah, much better. Okay, what is of interest here is, look at the combinations. These are the 4 characteristic parameters, linear combination of coupling constants, N, L, K, and N. And the N line and the L line determine strongly the spectral appearance. And you see the mesoform has an N value of -11 Hz and the racemic form of -1.8. And the L value has a value of -19 Hz, and on the right side, the racemic form of -28. So it must be very different. I have no time to go deeper into the NMR details, but the theory is evident. So let's go. We isolated 2 isomers because we were able to fractionate the crystals, and both show you clearly they are trans isomers. The phosphorus are trans. Now we see a 3-phosphinic acid. It's a terrible mixture, as you see on the left side. This is a PP COSY under proton decoupling. And we can work out the components, the number of components, and later on, by analysis, the percentage of isomers. And you see, as predicted, we find 4 isomers. One is 21%, 80, 28, 34, 17%. And they are simple A, B, C, or let us call it here X, Y, Z spectra, almost first order type. We can isolate 1 or 2 of the isomers. This is just one example. And what I want to show you is they are non-canonical rotamers. They are almost eclipsed. And this is typical for ethanes, these large substituents. It also exists in silicon chemistry. Yeah? And this analysis is straightforward. I don't need to explain that. The X-ray analysis helped our assignment. And you see that is a tris-phosphinic acid. You see the X-ray structure. You see that the numbering scheme of the X-ray. And below you see again the almost eclipse conformation. We can do the proton spectra, phosphorus decoupled, and of course we will see an APC. And if it is coupled to phosphorus, the proton spectrum is rather complex, but you can solve it with top spin easily. Yeah? Let us skip this. We go in the next step. This is the tetrakis phosphinic acid, tetra-isopropyl ester. Again, a mixture of isomers, but more than 6, because the rotamers are non-canonical. So there exists more species in solution state. And you see, that is what we predict if we assume a free rotation of, you see, 3 WXYZ, 2 XY twice, 1 X4, and indeed we will find that one of the isomers was isolated. You see the clean and neat structure of an WXYZ spectrum. They have slightly different chemical shifts, but still it is almost first order, not second order. And here we have a second isomer. In fact, it's number 3 of our evaluation scheme. And you see that is a symmetric one. That is an XY twice. You can analyze and you see the chemical shift width. No, the spectral line width is sharper links left than right. So this means the X nuclei here are sharper than the Y nuclei. And again, it is a non-canonical isomer. And the particular interesting case is this is almost orthogonal. This implies the coupling will be 0. And hence, it will have a simple spectral pattern. Sorry, now he stopped completely. Derek, is my time over? Or does it work? Do your best, please. Okay, thanks, sir. All those esters can be cleaved by concentrated hydrochloric acid. And we get the free acids. So we can make a monophosphinic, a bis, a tris, and a tetrakis phosphinic acid. They are archival. So not so exciting for the NMR spectroscopists, but for the analytical chemists. They do wonderful metal complexes, and they do pK titrations lead to stability constants or to dissociation constants. This is a tetrakis phosphinic acid where we have a phenyl group attached to the phosphorus. Since we have phenyl groups, they are sparingly soluble. And only if we add more than 2 equivalents of sodium hydroxide, we dissolve it. And this is called the parameter of degree of titration, which means molecules of NaOH by molecules of free acid. and you see singlets. Why singlets? Because the coupling constant by orthogonal coupling are 0. We cannot decide. So we only see the chemical shift of the axial position and the equatorial positions. And if you add more sodium hydroxide, you see there will be a line broadening, a characteristic, and the sharpening up. And in the end, this is a free anion, 4-, which shows 2 very sharp lines. The next slide. We wanted to have a very good soluble compound. So we replaced the methyl group by the phenyl group by a methyl group. And this is an analogous compound here, as you see on the left side. 4 phosphoruses attached to the ethyl skeleton, and the phosphorus here has a methyl group attached to it. And here we have a completely different situation. In the lower degrees of titration, means under stoichiometric amounts of sodium hydroxide, we have a fast proton transfer and a fast intramolecular rotation. And if you go to the upper titration degrees, you see the lines almost disappear. And it is most likely that we have a proton switch in this case here. And then if you titrate more, you get 2 sharp lines again for this situation. Yeah? Okay. I have shown you the X-ray structure as well, just to confirm our speculations. This is the X-ray structure of the tetramethyl group, which is in a solid state, almost like I showed you here. Yeah? It is not orthogonal in the solid state, but in the liquid state. Yeah? Next step. This is my university, and I come to the end of my lecture. Düsseldorf is a city of commerce, and we have a wonderful university. You are invited to come and see it. We have a big medical department, and we are the university founded by the Emperor Napoleon long, long ago. We got the golden key of our city, and we were made to a university. And it is still flowering, yeah? And I wish to thank my co-workers, Michael Batz and Angelika Getke, Michael Kronka, Wolfgang Küttelhaus, Johannes Ollich, Peter Reinemer and Harald Spiegel. They were involved in the technology of automated control titrations. That is what I wanted to show you from the technology. That's all I have to say, and thanks again for listening.
Okay, thank you very much. You didn't discuss so much the purification of the compounds.
No, I had no time.
Well, we have some time.
Okay.
I'm curious because it strikes me that this is very challenging work.
I had very good co-workers with golden hands, and they started just finding solvents and made a classical fractionated crystallization. And we got only few isomers, but not all separated. If we try high pressure liquid chromatography, the compounds stay on the column. They don't come out.
Yeah.
So I cannot use high pressure liquid chromatography. So I must do liquor in 30, 50 degrees and dissolve the compound, put it in a fridge and wait patiently until the crystals come out. And I'm lucky we got at least 2 from the 6 positives.
Right, yeah, because I thought chromatography is not going to be a good way to purify such compounds. So all crystallization, and then maybe comment a moment on the yields of the compounds. So is it just very small quantities, or could you actually purify modest amounts?
That so-called anomalous Michaelis Becker reaction, which we discovered, is a very versatile reaction. Yeah? And the yield is very high, in fact. You know? But the main problem is separation.
Right.
But we were interested, in the end, in the acids. And if you have a mixture of esters, and you cleave the mixture you end in the same acid. So it doesn't matter for us to separate it. We just did it for systematic methods to separate the acid.
Okay, thank you. Murux?
The chiral phosphinic acid what you have, especially the mono ones.
Sorry?
The chiral phosphinic acids.
They are all phosphinic acids, which I showed you.
Have you used them as other catalysts in any other reactions?
Sorry?
Asymmetric synthesis, using them? Asymmetric synthesis.
That's what it is here.
I'll clarify. I'll attempt to clarify.
Have you used these acids, these compounds for asymmetric synthesis?
No, never. I'm an inorganic chemist. My heart belongs to computers.
You did those beautiful titration experiments. Did you try to separate, I mean, your racemic compounds and their signals by titrating it with a chiral solvent so that you also distinguish, so to speak, the enantiomers?
Of course we did that. But then it is more difficult. If you
sure.
have a mixture, let us say, from 6 to more isomers, you know, and you add complexity by introducing a chiral solvent, you are lost.
Yeah.
In one or few cases, we tried it with a monophosphinic acids, of course.
Yeah. And you were successful in assigning also the peaks to the
No,
different...
not at that time.
Okay.
No. The assignment was made by X-ray crystallography
Okay.
or by molecular modeling, of course. Yeah.
Any final points? If not, please join me in thanking Professor Haigala.
Thank you for listening. Of course, you wanted that.
Okay, it's now my pleasure to introduce our next speaker, Professor Ramaswamy Murugavel. I know him as Murux. I met him many years ago at University of Göttingen when he was visiting there. Murux received his PhD degree from the Indian Institute of Science. He then did postdoctoral work with Herbert Roski at Göttingen. That's correct, I believe. And he has received a number of honors, including J.C. Bose National Fellow of the Indian Academy of Sciences, the Indian National Science Academy, and Royal Society of Chemistry. He's received several awards, and I won't list them here now. I'll let him get underway with his lecture. Professor Murugavel.
Do you mind if I stand here and talk? No?
It's okay by me.
So, I'll come there. Inviting me to be here. I really like to come to Rajasthan because 1/4 of all my graduated PhD students came from the state. I had students from all over place in Rajasthan, from Jaisalmer to all the way to Kota and Udaipur. So I'm really happy that I could come and see the place where my students actually come from. Okay, I'm going to stay on the theme of phosphorus chemistry because that has been the theme of the day, I think. Maybe Professor Bansal wanted to be like that. All the lectures have been phosphorus. But I will slightly have a small twist to the story. I mean, I'll be talking about the materials chemistry aspects of phosphorus. Mainly I'm going to stick around phosphoric acid and its esters and how these could be used for a variety of applications. It's going to be kind of a overview rather than digging too much deep into any one particular problem. Probably I would even beat Kumaraswamy. We packed 5 topics in one, probably I'll have more, but it's only a few short stories stitched together, but probably they'll have some link with respect to each other. And let me skip this slide. I'm a synthetic phosphorus chemist, so whatever I do revolves around making molecules which have phosphorus in it in some other form. Only thing is, over the years we have learned how to put this synthetic products into something which is useful. Way back in the late 90s when I started in IIT Bombay, my independent career, I looked at phosphorus acids as the precursors to build thermally labile polymeric compounds which could be actually transformed into ceramic materials at very low temperatures. From there we moved on to make some phosphate-based metal organic frameworks. That's because of the rush we had saw towards the turn of the century when people started to make carboxylate-based MOFs, so we had our hands on into the phosphorus-based metal organic frameworks. Recently we also work on even phosphorus-free cold organic solids, which probably I would not touch upon today. Of late, we are looking at the molecules that exhibit unusual properties. If time permits, I'll probably give an example of molecular magnets. So let me begin with the first topic, namely nanoscopic ceramic materials. These compounds are polymeric materials which actually undergo very facile thermolysis at very low temperatures and produce ceramic phosphates at temperatures often below 300 degrees centigrade. Normally, when you make a metal phosphate or metal silicate material, you use a furnace and you anneal and you go through rather high temperature processes, often in excess of 800 degrees and above. Okay, this is what I just said. Like a phosphoric acid, for example, combines with a large number of metal ions. In fact, every element in the periodic table under a variety of conditions and form metal phosphates. They have enormous amount of applications which I'm not going to catalog down, other than to say that much of this high temperature synthesis spit out materials which are often impure, contain more than one phase, because that phosphoric acid forms ferrophosphoric acid, metaphosphoric acid. So all these happen at high temperatures, so you get a number of phases. So often phase pure materials are very rare. Years ago, we recognized that there are compounds in the literature. In fact, a paper published in 1960 by Harris and co-workers in Journal of Chemical Society talks about this one particular compound. In fact, it is kind of among many esters that have been described in the paper. This compound was described as something which is useless because you make it and keep it on the table and go for a coffee and come back, you have phosphoric acid. It's thermally unstable. And if you think you're smart and if you put it in the absence of water, even if you exclude water, it undergoes facile thermolysis or beta hydrogen elimination because it has 9 to 18 beta hydrogens. Any of one of these 18 hydrogens can bite back the phosphorus and form isobutene. As a result, you get phosphoric acid. So instead of doing reactions with phosphoric acid at high temperatures and make metal phosphates, why not start with this particular diester? Because it pretty much looks like a carboxylic acid. If you make a metal acetate from acetic acid, whatever happens, it should happen with this because only the carbon is replaced by phosphorus here. So this part you can make a metal complex, and it is hydrophilic on this side of the side of molecule and hydrophobic this side. As a result, this compound is amenable for synthesis in a variety of solvents, starting from pentan on one side and to water on the other side. So I call them as a kind of organic soluble form of phosphoric acid because of its both hydrolytic and thermolytic instabilities. So I'm going to cut a long story short and just show in one slide what we did over 6 or 7 years, several PhDs. We just kind of made several, dimensional solids, 0-dimensional cages, 1D polymers, and 2D networks, and made some models for biological systems. And one common theme running across all these materials, don't worry about what they are, what structures they are, but the only point to remember is that it is pretty much inorganic compound with only 2 organic groups, namely ditertiary groups, which undergoes facile thermolysis. After making these compounds, you can easily thermalize and make a material of your choice. Depending on what is your metal to phosphorus ratio in the starting material, you can get a variety of phosphates. And since you work with the molecular systems, your thermolysis is clean, neat, and you get only one material. Just show one example. This is a cadmium phosphate polymer made from ditertiary phosphate. This is a one-dimensional polymer. It's pretty much like an iron tube or iron rod coated with paint, something like that. So you have 2 metal groups at the top. Now we can actually take this and heat it up. And just look at the temperature at which the organic group walks off. At 140-150 degrees centigrade, you lose all the organic content as the isobutene gas. It's a very nice byproduct because you don't have to really work up, it just goes off. And then the condensation of the surface pH groups takes place between 200 and 300 degrees centigrade, and you are in business at temperatures as low as 300 degrees centigrade. You can do this with essentially every metal in the periodic table, and you can actually follow these reactions by in situ X-ray diffraction or in situ spectroscopy. It could be phosphorus NMR, it could be infrared. As you can see, this is a metal organic polymer, you get an inorganic polymer, then condenses, and at 350 degrees centigrade you have the nanoscopic phosphate, then this crystallizes. So the theme of the entire work was to make condensed phase materials, now often in the size regime of somewhere between 5 to 20 nanometers. You can use them for a variety of applications, which again I will not dwell upon. At this point of time, we thought that we are actually blocking 2 of the 3 possible protons in the phosphoric acid by 2 tubular groups. Suppose if I don't do this, I have one more hydrogen there for me, then I can have a PO3 2- anion, which will be used for building larger structures which are non porous. So you can go from a condensed matter to which are highly porous phase. Okay, I'll just give you a small look back. I think why we really got into this, and I'll talk about our strategies and give a couple of examples. This one slide it just summarizes about 250 years of porous solid science. Zeolites have been around for nearly 260, 270 years, with the accidental discovery of this class of materials by Baron Kronstedt in Scandinavia. And then, in fact, I was told that he wrote a small article in a Paris newspaper and forgot about it. Only after 100 years it got picked up and people worked on it. 1926, people found out that zeolites do have 5 angstrom channels which could be used for different purposes. Soon followed is the first chemical synthesis of zeolites from indium carbide, and years later, I think Edith Flanagan, through 2 of her very important discoveries, showed that silica could be porous, and then she said that you can completely take silicon out of the system and make only phosphorus-containing porous materials. These are the well-known classes of sapos and alpos and such materials which are porous and do a lot of functions. And there was mesoporous materials in between, and the hell really broke loose with the articles of Omarayagi and Robson on metal ion frameworks which use metal ions and di and tricarboxylic acids. But one commonality right from the accidental discovery of zeolites by Kronstedt, which was actually made by nature through volcanic eruptions, to the synthesis of modern morph materials, is the brutality that is required to make these materials. You put the ingredients A, B, C, D in a jar, shut it and put it in an oven, pray God for a few days, and then take it out and see whether you have any crystals, and then use them for some purpose. So being trained as synthetic chemical chemists, we wanted to ask a question that whether one can actually do a rational synthesis of these zeolitic materials, because Edith Flanagan has already showed that you can use phosphorus as the basis or phosphate as the basis and build porous solids. So the one disadvantage is with this, to say that phosphoric acid, as you know, is a tribasic acid. PO4 is 3-. If you want to make an hydrophobic material, the cation has to be 3+. The periodic table does not contain too many 3+ cations. It does have the lanthanide series, but they form large coordination numbers 9, 10, 11, 12. You cannot stitch porous structures using that. And you do have elements like gallium, indium, scandium. These are expensive. You don't want to use them. So essentially, whatever porous solids you want to build with the phosphorus is restricted to the use of aluminum. So suppose if I'm going to block out one of the tribasic acid protons of phosphoric acid, and I have a PO3 2- instead of PO4 3-, I can call upon all the first order transition metals, namely zinc, iron, manganese, cobalt, nickel, so on and so forth, and build materials which are magnetic, materials which are catalytic. So that was the idea. So what we did was, this slide is just to show that I think one can actually start from simple tetrahedral systems like PO4 3- and combine them as a corner sharing ensembles or structural motifs, and then build upon these structures. So you can actually do a retrosynthetic analysis and you can build any of these clusters. Then you are in business to assemble them into porous materials. That was actually what we did about 10 years ago. In fact, we wrote this scheme in an article we wrote up when we concluded the work on the ceramic materials, that one can actually extend this chemistry to porous solids, and we showed this cartoon about 15 years ago. And soon later, I think we did a small adjustment. This already I spoke about it. So if I can only compromise one of the acidic protons by an R group, the R group should be large enough. It should impart enough solubility to the system, and so that I can do reactions in organic medium rather than in water at high temperature. So it becomes lipophilic. So again, we found a compound in the literature which is again described by an organic chemist way back in the 70s, which uses the 2,6-diisopropyl phenyl group. As Professor Hegel said, whenever you have isopropyl groups, the compounds crystallize very well. Okay, you can have a cubital group if you want. They start rotating in the extra structure, then you have to model them in this order. But isopropyl nicely locks, so you get good crystals. So and also has 2 organic groups like that ditetrahedral group I had before. So it gives solubility, also gives the handle to easily crystallize these compounds. Initially we were working with metal alkydes like dimethyl zinc, dimethyl cadmium, and so on and so forth. And soon we realized that you don't even need metal organometallic reagents. You can do with acetates. we were using dry THF and dry hexane towards the reaction, then we realized even drum methanol is good enough, and we did prepare the double 4 ring, which was shown to be one of the nice building blocks. And then we crystallize this and convince ourselves and others that we do have a cutout of a zeolitic material as a soluble molecule which can be used for other purposes. Again, I'll just cut a long story short to show that we used this building block and used several chemical groups what we know of, namely hydrogen bonds, covalent bonds, covalent bonds, and made a variety of porous structures. I will just only show a couple of examples. This is one of our early work about 10 to 12 years ago. We published it as a communication. We showed that I think you can simply use pyridines which contain additional functionalities like amino or phenolic moieties or even methanolic ethanoic moieties as the source of forming hydrogen bond between the cubanes. We actually engineered the number of what I call as intra-cubane versus intra-cubane hydrogen bonds and built either a railroad or a honeycomb or even a 3D structures. These are look like materials, but as you know, here the glue between the building blocks are only hydrogen bonds. They are fairly stable. The idea is good, but can't be used for many applications. So we fell back on some of the developments that have been happening in the morph chemistry at that point of time, and then started to use ditopic spaces such as bipyridine. This is just a cartoon, just to show that it's more of a drawing board exercise before we get into the work, because you can actually equate this cubane as a tetrahedra of 4 zinc atoms, where 4 of the zinc atoms have coordinative unsaturation. If you can knock off these level ligands, normally a methanol or a DMSO molecule, by a space such as this, you can build a super hexagon from which you can actually extend in along the X, Y, and Z axis and produce a diamondonoid kind of pyramidal structures, which will have nice pores in the order of about 30 to 40 angstroms, depending on what is the separation between the 2 nitrogen atoms in this particular examples. Okay, so again we did this a number of examples. Then we connected 1 cubane to 4 cubanes through this bipyridine bridges. Depending on how we place these cubanes with respect to each other, we can make isomeric compounds. For example, you can either have a diamond-like framework solid, which is this, or even you can have a Kagome type lattice where you have a micropore, which is about 7 angstroms, or a mesopore, which is about 30 to 40 angstroms. Then you can play around with your knowledge of organic chemistry. You can build some of these molecules in the lab, or you can make your own ligands, and you can change the separation between two nitrogens from 7 angstroms to almost to 25 angstroms between the 2 nitrogens. In the process, you make them as electro-responsive, photoresponsive, and make frameworks which can be used for a variety of applications. I'm again not highlighting those things. As you can see, whatever I have been speaking so far, use the zinc to zinc connection. Essentially, you take these building blocks and only make bridges between the 2 zinc atoms using bipyridine spaces. Suppose if I were to actually use all the 8 corners, that is the 4 phosphorus corners as well as the 4 zinc corners, the framework would look like this. These are very hard structures to even think of, but how do we do this? That's when I had a student joining, actually from Rajasthan, Kamala Sharma, who joined my group, and she did a small adjustment to this problem by synthesizing a para-substituted phosphate ester. Essentially the molecule is the same, other than that she nitrated the ring first and then she reduced the nitro group into amino group. So now we have planted an NH2 group here. The chemistry that followed was exactly the same as what we had before. Other than that, there was a small twist. So now the cubane contains the same sexual motif. Other than that, 4 NH2 groups are just pointing to the 4 corners of the tetrahedra. And you can actually do this reaction in the presence of a ditopic spacer. Now you get a zeolitic material. This is a covalently rich zeolitic material which has been flooded with number of functional groups, namely NH2 groups. So the surface NH2 groups can be used for scavenging of acidic molecules such as CO2, SO2, and so on and so forth, which actually we do. Okay, and more interesting actually was, now this is how this looks like, that there are nice channel structures where the NH2 groups are nicely decorated along the walls of the channel. So essentially you can actually, the linear molecules such as CO2 and SO2 can be easily absorbed, and in fact they show about 18% of CO2 absorption in this. This is another topic, I will talk about it in a different occasion. So what was more satisfying, as I said, was when she did this organic derivatization. And she was actually having a problem with the solubility of the compound NH2. She wanted to protect NH2 or something. She put an acetyl group there by using acetic anhydride. But now, instead of going through several steps in one part, she could actually link 1 cubane to 8 cubanes, the PO3H2 part of the molecule actually forms the cubane, and the carbonyl that is hanging as a tail actually bites the nearest neighbor. So essentially each of the cubane contains 4 coordination to the phosphorus and 4 coordination to the zinc. As a result, you have a 8 connected network. Something that has been not seen before in any of the porous solids that have been made so far. Even the MOFs contain a maximum of 6 connectivities when you have an octahedral structure. So this is how the structure looks like. A cubane connected to 8 cubanes, and each of these cubanes is connected to 8 more cubanes. As a result, you have a wonderful, again a diamondonoid, a double diamondonoid structure, which can be porous and which are actually functional because you have in this group, and you can use them for a variety of applications. So just as submitted, I think though this looks like, I think very soon they should appear in the journals. So just to move on, to just change the gear a bit. How are we doing time, Derek? 10 minutes? 10, 12 minutes?
Yeah, about 10 minutes.
10 minutes, okay. So if you noticed that I had 4 amino groups pointing towards the 4 corners of the tetrahedra, it immediately looks like an organic molecule you normally used to. And in the case of this is what I think we used. We used hydrogen bonds as a strategy and made frameworks. These are for solids. Then we use the datopic spaces borrowed from the MOF chemistry, and we made these networks. But now there's something else that we've been developing the recent years, in the last 10-15 years, using molecules of this type. Tetraamino methane or tetraformyl methane. Could be silicon or could be carbon. Doesn't matter what it is. These are tetrafunctionalist molecules. You can actually look for the complementary functionalities. For example, an amino group and a formal group can combine and give you a imine. So you can use this as a linkage and form for solids which do not contain any metal in it, but these are what are called as covalent organic frameworks. But we saw our molecule something similar to what has been described in the literature before, because there are 4 zinc atoms, this cubane, in the corners of corners of tetrahedra, and the 4 formal groups are just protruding out. So exactly that's what we did. We took this molecule. This is the synthesis of this molecule. I'm not going to spend time on that, but to show that we took this molecule and then combined it with diaminobenzene and its higher congeners like benzidine and the substituted benzidine molecules. And the picture is pretty much same as what I showed you a while ago, where I had a super hexagon. Other than that, the wall of the the connector was a simple bipedal molecule with no functionalities. But now I have 2 imine groups here. That means essentially this framework is loaded with a large number of imine functionalities. In inorganic chemistry nomenclature, it will be a ship base. You know what a ship base can do. You can actually anchor small metal particles and nanoparticles and do further chemistry with that. So this is what we did actually. And when we actually introduced isopropyl group, again the same strategy as what was spoken about, you can actually start growing single crystals. Often these materials are amorphous, you don't see too much crystallinity. But when you load this benzene with the isopropyl group such as this, and expand, you pull this out a little bit more, you can actually crystallize these compounds 5 and 6. I'll just show you only one example where we actually, this is again to show that these are isostructural, only differing from each other by the distance between the 2 qubits. Okay, and you can use them for a variety of organic reactions. I just showed one example here. What is important here is that these are microcrystalline. These nicely, come as, like something like a broccoli or a cauliflower kind of a structure. And if you actually pluck one of these, small single crystals, which is only about 10 microns by 10 microns by 50 microns. And if you have a good X-ray beam, you can even get a structure. That's what we did, and it showed that these do really have a diamond and a network. And as I said, these walls are, both hydrophobic because of the group, as well as functional because of the imine groups that are loaded. Okay, currently we are, pretty much what Professor Gates showed in the morning. The polymers was loading gold nanoparticles. Now we can use these porous solids because the walls are functional to hold on to the gold clusters, which are not really big. Even sub-nanometer species could be easily absorbed in this. And this I'm doing with a colleague in IISER Pune. Okay. So just in the next couple of minutes, I'll just talk about one problem I've been facing all along this chemistry, maybe 30-40 papers in this area. 3 references for each paper. Each of them would ask the same question: how do you form the double 4 ring? Is the double 4 ring is a kind of a spontaneous formation by 4 of the anions and the 4 of the zinc atoms coming together from the solution and then self-assembly, or there is some kind of hierarchy that goes on in the system. Because we have been always claiming this is a hierarchy because the smaller rings form the double ring forms zeolites. So there was no proof of hierarchy. So two of the PhD students were given the task of actually unraveling what goes on in this. So we again went to the drawing board and drew the possible ways of combining these hierarchical structure. Assume that the first step of the reaction is that two phosphates and two metals form a small 4 ring, which should look something like this. This was actually absent in our system for a long time until we dumped loads of either pyrazole or imidazole into the system and brought this dimerization, and we got an example. I mean, as we would expect, the two pyridine O's were trans to each other. This is not an organic molecule, this is an inorganic molecule. Each edge represents the ZNO-P moiety. Either you can have a face-to-face dimer formation to use the usual suspect, namely the double 4 ring, which we get 99% of all our reactions. But if this were to be the structure which is, for symmetry reasons more stable, one would not actually close the cube, one would rather get a tub. This tub would actually then can be placed next to each other and form something like a square wave polymer, but a two-dimensional polymer. Or it's too much to expect that they will come only face to face, they can come even randomly and can form a side-face polymers. So we actually went out to hunt for these, so far unisolable polymeric species of the same system. Again, we used Serix as a handle. I'm not going to talk too much about that. Then we have isolated a dozen examples of this square wave polymer and a few examples of this, so-called step polymer or a zigzag polymer. And the moment we got a zigzag polymer and even wrote a paper on this and sent it out for publication, now the referee would actually ask a very nice question. If you have to have a zigzag polymer, by using a template you should be able to fold around and realize so far hitherto unknown species like a double 6 ring or a double 8 ring. So we went around looking for suitable templates to fold this around and make bigger drums. There's a reason to look for these bigger drums rather than the cubanes, because I showed that the cubanes can be connected at the 4 zinc atoms or at the 4 zinc atoms and the 4 zinc phosphorus atoms. So you can have a gate connection there. Now if you translate that to here, you can have 6 plus 6, 12 connectors, and you can have here 8 plus 8, 16 connectors. These are unheard of or unseen so far in theoretic science. Their topologies have been worked out. So we thought it would be really great starting points, especially to make so-called microporous materials, because to hold on to small molecules like hydrogen and the CO2, you don't need bigger voids, but we need closely spaced walls, but with some micropores. So that was the reason to hunt for these molecules, and we are really lucky after a few years of struggle to synthesize both molecules in one very busy crowded slide. I just showed that we used the Serix as a handle. We played around the substituents on the aryl group, and we sometimes use the solvent as the medium. We use templates, and then we finally assembled a double 6 thing and showed that these structures do exist. And we are even fortunate to have 6 formyl groups, because of formyl pyridines these are, and 8 formyl groups here. That means straight away we are in business to make the cough-like mouths or mouth-like coughs by using the imine methodology. If luck would have it, I think we could even make, you can use the other 6 or other 8 centers, you can have these bigger structures to come. But I think that's it kind of summarizes our efforts on building porous solids using a simple phosphate diester, namely phosphate monoester, namely the diisopropyl phenyl ester of phosphoric acid, and using a variety of metal salts. I stated all along in my talk zinc as a metal. This is not restricted to zinc. I use zinc for all the examples because zinc is diamagnetic among all the first order metals. So you don't have the problem of doing EPR and magnetism to prove that you have this compound. So NMR is good enough. For example, here you can see the solid state solution NMR, how the structure is actually dynamic with the extra water molecules swimming around and producing some inequalities among the 6 phosphorus centers. So that's what this looks like. You do have a single 4 rings. There is an hierarchy, we believe at least. I think we are convinced. And then this hierarchy leads to tapes, and the tapes can be folded around at any point of time and form drums. And if you're lucky enough, I think we could even isolate the larger structures. So what I'm going to do is, in the interest of time, skip this exactly. Can someone skip from my slides? I will do here, so no problem. Yeah, just skip this. Just give you one word. We just now remove the hydroxyl groups and put the amino groups, so that these protons are not anymore as acidic as these are, the only center which can bind to metal is the oxygen. So use them as a a ligand in the lanthanide chemistry, and we made recently some fantastic magnets. I think that's a bit of physics to introduce, so I will not talk about it. So we have some of the magnets which show openings up to 30 Kelvin. This is another topic. So I just go back to the last bit. It will probably take a minute or two. Now we are extending this stuff to even more interesting current topics, namely to make perovskites which are based on phosphorus and self-exfoliating 2D materials. Just one example each. So a failed attempt some years ago, I think we saw some analogy between the formates and the hypophosphates. A couple of groups, Songos from Beijing and Tony Cheetham from Cambridge showed that you can make formate-based perovskites. We saw some analogy between hypophosphite and the formate in terms of size. The tolerance factors were calculated, and we doing all the reactions in the organic medium mainly always ended up in porous solids. Later we collaborated with Tony Cheetham himself and then made the first family of hybrid perovskites. We are now looking at them as multiferroics and ferromagnetic materials. The chemistry is a developing chemistry, but this phosphorus can be even put into our solid state material, and this could be interesting in the years to come. Very recently in unpublished work, now we have used a monoalkyl phosphate. A monoalkyl phosphate as a handle. I think here. This is isopropyl. We heard about that diisopropyl ester. This is a monoisopropyl ester. As you can see, you can build a 2D material such as this. The interaction between the two layers are only van der Waals. There's nothing more than that. It's like a sheaf of papers. You just blow the air, they go into pieces. They're self-exfoliating systems. You can just put it in the solvent. Immediately it goes into pieces, and you do a mild sonication. You can get a 2D materials which can be scrawled, which can be folded around, made tubes. It can be hybridized with the graphene, and you can use them as a battery materials and other purposes. This is again a work which I am doing with a colleague in ISF Pune with Vaidyanathan. I think this is as you can see, these are highly layered structures, and we are fortunate to get to some single crystals and show this ahead. So this is how it looks like. You do a sonication 5, 10, 20, 30 minutes, and 40 minutes at 10% power of sonicator, you get truly single sheet, 1.2 nanometers over 12 angstroms, which is the unit cell length along the C direction of the crystal itself. That means we have one-dimensional solids. And that's a good point to stop, just to tell that the phosphoric acid can be used in many ways. The old phosphoric chemistry was just to use the metal phosphates, which are ceramics. Now we make porous solids with that, we make props with that, make larger building blocks, we can make perovskites and 2D materials. There are many other topics for which we use these materials which are not touched upon today, namely as sensors and ion scavengers. I think essentially it's a good synthesis. If a student is willing to do, you can actually find application for it. I think at this point of time I will stop by thanking my group. Much of the work was done by Sandeep Gupta and Kamala, has already left the group, so the photo is not here. And there's another person called Pratap Bishnoi, I think, who also left the group. So I thank the funding agencies, DST and BRNS, and all my students. And much of the critical preparation come from my colleagues, both Radharaman and Patwari. And thank you.